So far, in the sequential circuits, we have discussed about different types of flip-flops characteristic table, flip-flop excitation table, conversion between different type of flip-flops. That means to convert one type of flip-flop into another type of flip-flop. And followed by this, we in the last few lectures, we have discussed about the shift registers. Shift registers are used to store the temporary data in the processor. And in today's lecture, we are going to discuss about the counters. As clear by the name, counters are the circuits which are used to follow or a particular sequence. Now let's come to the definition of the counters. Counters are sequential circuits which count through a specific state sequence. They can count up, count down, or count through other fixed sequences. And as far as the type of counters are concerned, there are two distinct types of counters, and commonly known as the first one is ripple counter. In the ripple counter, clock is connected to the flip-flop clock input on the LSB bit, least significant bit flip-flop. For all other bits, a flip-flop output is connected to the clock input. That means we can say only single clock is given to the very first flip-flop, and which is a LSB of the counter. When we are going to discuss it with the help of different circuit diagrams and the timing diagrams, it will be more convenient to understand. Now, for all other bits, a flip-flop output, that is the previous output of the flip-flop, is connected as the clock to the next flip-flop. The circuit is not truly synchronized, or we can say it is ripple counter is also known as asynchronous counters. The output change is delayed more for each bit forwarded to the MSB and resurgent because of low power consumptions. So these are the ripple counters. And the another type of counter which is used, that is a synchronous or parallel counter. The clock is directly connected to flip-flop clock inputs. That means clock is common to all flip-flops. That's why synchronous counters are also known as parallel counters. Now here, to design a logic to a synchronous counter, logic is used to implement the desired state sequence. So as far as the design is concerned, ripple counter is pretty much easy to design. While when we are going to design the synchronous counter, it requires a lot of manipulations and logics to design the synchronous counters. Now today we are going in to discuss both type of counters, how to design and how they works in this lecture or in the some coming slides. Now the use of counters can act as simply clocks to keep track of time. You may need to record how many times something has happened. That is again stored in the counters. How many bits have been sent or received. How many steps have been performed in some computations. So these all are are done with the help of counters. All processors contains a program counter, as you have been studied in your C when we are discussing about the architecture of the ALU, arithmetical logic unit. All computer has a program counter, and the programs consist of a list of instructions that are to be executed one after another. The program counter keeps track of the instruction currently being executed. Further, the program counter increments once on each clock cycle, and the next program instruction is then executed. So this is another use of the counters as program counter. And further, a counter may be used as a frequency divider. When we are going to discuss in the next some slides, then we'll see the how a counter can be used as a frequency divider. Now the very first is 3-bit ripple counter. So again, as we know that flip-flop is a single bit storage device. So when we say that 3-bit, that means we are using 3 flip-flops and the number of states are 2 raised to the power 3. If there is a n bit counter, then the number of state are 2 raised to the power n. And in this case, when we are using 3-bit ripple I am using, that is the asynchronous counter. Up counter means it will starts from 0 and go to the 2 raised to the power n minus 1. So when we are using 3-bit, it will starts from 0 and go up to 7. So the sequence will be 0, 1, 2, 3, 4, 5, 6, 7, and after 7 it will again return to 0. So this is the counter sequence. This counter is also called as asynchronous because not all flip-flops are hooked to the same clock. That means clock is different for every flip-flop. Whenever clock is common, then it is said to be a synchronous or parallel counter. It should be kept in mind. So you can see here in the state diagram, we start with the state 0, 0, 0, that is the initial state. Then go to 0, 1, 2, 3, 4, 5, 6, 7. Then we go to the again to the 0. So this is known as the state diagram. So here is the circuit. What we do, the design is pretty much simple. We are using for design of the counter, either we use say a T flip-flop or a JK flip-flop. The connections are same. What we do, that all inputs of the T flip-flop are 1. First flip-flop is fed with a master clock. Output of the first flip-flop is the clock to the next flip-flop. Output of the next flip-flop is the clock to the next flip-flop. This Q0, that is the LSB, least significant bit of your count. This Q2 is the MSB, that is the most significant bit of your count. So when we are designing the up counter, keep in mind for the asynchronous design, the input of the T flip-flop or the JK flip-flop, J equals to K equals to 1 or T equals to 1 for all flip-flop. First flip-flop will be given a master clock, and the output of LSB is the clock to the next flip-flop, and the output of the next flip-flop will be the output of the MSB. So in this way, this is the simplest design. This the flip-flop which is fed with the master clock is the LSB, and the outer last one is the MSB, most significant bit. So here we have used bubble, that means a negative, and this triangle represent that is a negative edge triggered flip-flop. Now come to the timing diagram. Here are the counts. This is your master clock, and I have marked as arrow at the negative edge, means whenever the clock comes from whenever clock comes from 1 to 0, that is the triggering pulse. So at the time of the transition from 1 to 0, there will be a triggering, and we can look into the circuit that we have put all inputs as 1. That means that is the benefit of T, that is a toggle flip-flop. Whenever input is 1 and an active clock is given to the flip-flop, the output will toggle. If it was previously 0, it will be 1. If previously it was 1, it will be 0. So we are using so here we are using the benefit of the toggle flip-flop, that whenever input is 1 and with an active clock, the output of the T flip-flop will toggle, and that will be pretty much clear when we are looking into the timing diagram. So here you see the timing diagram. For the first, that this is your Q0 is your LSB. Initially all flip-flops are reset, that is 0, 0, 0. The initial value is 0. Now we are coming from here. We are looking only for the first flip-flop. Input is 1, that is T is 1, and clock is, here is your clock. So whenever clock is active, that is negative edge, the output will toggle, and then we look only into the first Q0, that is the LSB. Initial value is 0. First clock is here. Whenever first clock, the output changes from 0 to 1, and it will wait until the next clock is fed. For the next clock, here is the second clock, negative edge, the output will change from 1 to 0. It will be 0 until the next negative edge is fed into the flip-flop, and you can see that at third clock it will change from 0 to 1, fourth clock 1 to 0, fifth clock 0 to 1, sixth clock 1 to 0, seventh clock 0 to 1, and eighth clock 1 to 0. So you can see that wherever there is an active clock, the output is continuously changing. Now you can see that from this side, from beginning of the clock till the next beginning, till here, we can see that this is the cycle time period, and you can see for the time period of the Q